Welcome back to our video lecture series on statics. Now recently we've been talking a lot about projections and forces and torques, but thus far the types of problems we've had, you don't really need to know the projections. We've just been giving you fairly simple concepts so you can get an intuitive grasp of what they mean. However, what I'd like to throw your way now is a problem that we can play with so we can actually learn how to use these projections. We see how powerful they are. All right, so imagine that we have in front of you a cube. Now, right now it's a cube, 2 units on each side. And as a matter of fact, what I'm going to do now is I'm going to change the dimensions on these sides. And the reason I'm going to change the dimensions is so that when we run our numbers, it becomes clear to you which is which. Let's just say 2 is our z-axis, or I'm sorry, is in our z direction. We'll make this 3 and we'll make this 4. And the problem I want to send your way is we have this force being directed at point D. Imagine it's like a cord that's being pulled, and it's being pulled towards E, so like at a 45-degree angle. And if we can imagine, all right, well, what are the components of that force, etc. But now what I want to do is I want to change it a little bit. I want to say, imagine that this cube, or this it's not quite a cube, but this block is constrained along DH. D is in delta H. It's constrained. You can imagine that there's, a rod going all the way through the tube from H to D, and we're going to apply this force. Well, it's not going to move in the horizontal direction. It's constrained along DH. How much of that force acts on DH? We're going to figure that out. The next thing that we'd like to take a look at is we could figure out the moment that F has around point A. No problem. Well, what moment does F have around an axis AC? Let's say we put that rod through AC and we apply the force. How much torque is going to be applied? Now that one actually isn't too bad. That's something that we could solve with our original cosine theta, where you just intuitively can navigate your way through. However, let's change it a little bit. Let's say that rod goes from A to G. Okay, so it's very similar to the DH rod, but we have a rod now going from A to G. What type of torque does that force bring about? Now these problems, if you were to do them just using your cosine and sine theta the traditional way, they'd be pretty tricky. So what we'd like to do today is we're going to use our rules of projection. We're going to use our cross products and our dot products, and we're going to identify how much of this force is being applied and in what direction. Now I do need to clarify one thing. In the beginning I said that force F goes from D to E, and it will. I said that was a 45-degree angle, but as soon as we change that from a cube to just a block, it's not a 45-degree angle anymore. We need to figure out exactly what angle that is. But in the end, it does go from D to E. That said, let's get started. All right, let's first find out, or let's do a quick review of what a projection is. If we take F, the force, times dot product times the unit vector, say from A to B, that is the projection of F on, we'll say AB, in the direction of AB. That means what component of force is acting in the direction AB. We can do the same thing with a moment. This would be the moment about A, or the moment about any point on this line, to the dot product with the unit vector is the projection of the moment about A on AB. So this kind of reminds us what we're dealing with here. Let's start off with the forces. What is first, what is F? What is the vector? Well, we know that the overall magnitude is F, okay? And we know that it's acting in this direction plus this direction, all right? Well, this direction is 2. This vertical direction is 3. So what we need to do is find out what F is as a vector. The first thing we can do is we know its direction. It's going to be in the negative. Well, let's do positive first, or J first. It's going to be 3J minus 2K. That's going to be its direction, and its magnitude is going to be F divided by this magnitude of whatever 2 squared plus 3 squared is. So, or the square root of 2 squared plus 3 squared. That's going to be 4 plus 9 square root of 13. Okay. So this is the magnitude of that direction. We take the direction divided by the magnitude of the direction, and here we can even do the magnitude of the force. And here we have what that vector is. Or if we wanted to say equals F over square root of 13 times 3J minus 2K. We want to get this in vector form as soon as possible, because the next question I'm going to ask is how much of the force is directed along DH? How much of the force is directed along DH? Let's put that in a different color. Here. Well, we know that that's going to be a projection. Go ahead and see if you can figure out what the solution is to this. I'm put the video on pause, and when you come back, I'll have everything written out. I hope that was a good exercise for you. I'm going to scroll down and take a look at what we did. First, I wanted to find out what the projection was, so I took F dot the unit vector. Oh, sorry about that. That should have a, it is a vector. The unit vector from D to H. So F as a vector is F over square root of 13. Square root of 13 is its magnitude. We've already gotten that. Times 3J minus 2K. And now I'm going to take the dot product. Over here, I found what the unit vector was from D to H. You take the vector of D to H, divide by the magnitude of D to H. Should already have that covered. And once I've put that in as the unit vector, I simply take the dot product. There's no I in the first term, so the I drops out. The second term, we have a 3J and a 3J, so that's 9. A negative 2K and a negative 2K, that's 4. We multiply the square root of 13 and the square root of 29 to get our magnitudes right. We simplify these numbers, and we find out that it's 0.67F. That means that 0.67F is the magnitude of F going along this line. If we wanted to say, well, what is the vector then of the force? We would simply take the force directed along the unit vector. So we'd take 0.67F, multiply or divide by square root of 29 here in this direction. Negative 4I plus 3J minus 2K. It'd look like 0.67F square root of 20 over square root of 29. And we could simplify that too if we wanted to, just to, or not simplify, but calculate that out so we just have one term in front of the F. And that is the vector force F along DH. Hopefully that's what you ended up with. Now I wanted to show you one more thing. One of the questions that might come up is, what is the angle here? What's the angle between the applied force and the constrained, its constraint, where it can move along? The way we find that out is we go back to our original dot product definition. Dot product equals magnitude of one times magnitude of the other times cosine of theta. Well, we're going to use this cosine theta. we know that the dot product of F dot lambda dH is 0.67F. That's what we were trying to find out, right? So that's 0.67F. We know that the magnitude of force F, well, is just F. The magnitude of the unit vector, that's always 1. Divide both sides by F. 0.67 equals a cosine of theta. Theta is 48 degrees. So that is the angle between the force and dH. Our next problem is, let's figure out, so we've looked at the force and how that can work. Let's take a look at the moment. All right, what is the moment about A? The moment about A. We're going to go down 3 over, it's going to simply be r cross F. R will be down 3 over 4, and F will be its normal vector. So let's see if we can fit that in right here. Moment about A is R cross F. Now let's see, that was R was in direction, it was negative 3j plus 4i. And we're going to cross that, we're going to cross that with F over square root of 13 times 3j minus 2k. And the magnitude of 3 and 4, that's going to be a 5. So we're going to take that 1 over 5 to make sure that, oh, sorry, we're not doing a unit vector. Sorry about that. Nope, we're fine. Negative 3j plus 4i, let's make sure that's right. Down 3 over 4. Now we simply run the numbers. Go ahead and do it yourself. Put this on pause, and I'll have the result for you. Let's take a look at what we have here. We ran the numbers, and we find that the moment about A is 2 times the force divided by square root of 13 times the quantity 3i plus 4j plus 6k. That is our vector, our moment about A. Now we have just enough time that we can say, all right, let's take that moment and let's see how much of that, what if we constrain that along AC? Let's constrain that movement along AC. Now, what type of moment is going to be applied across that axis? Now, AC is only working in the I direction. So for moment about AC is simply going to be the projection of the moment about A along the unit vector AC. Now AC is just the x-axis, so that's going to be an easy one to do. We're going to take our moment, and that's 2f over square root of 13. I drew out that 2 from the ijk just because it reduces those numbers a little. You don't need to. You could do 6i plus 8j plus 12k. And now we're going to take the dot product simply of 1i. That's a pretty simple one right there, right? So if we do that, we're going to, the j and the k, nothing's going to happen. We're going to multiply 3i times 1i. So we're simply going to end up with 6f over square root of 13. So this is the amount of that moment that would be applied if the block were constrained along the AC axis. Stay tuned. On our next module, we're going to continue and say, what would the moment be if we constrain this block along the AG axis? Go ahead and press play on the next one. When you're ready, I'll talk with you.